now see the second method to derive the formula for the velocity of a transverse wave, a longitudinal wave. Here doesn't matter the shape, and then we will have the general formula. So here we have our string. When it is in motion, let's say we have it on, for example, something like this, and we are taking the extreme points, so here and here. We have the components of the force. We have the component on y, F sub y. Here we have the tension of the string. This was the force on x. This is the resultant component. Here we have the force on y, the tension of the string F, and this resultant vector. So the component in x are going to cancel, so there is no net force on x because the all have the same tension on the string on the x direction, so they will cancel. And for F sub y, the net force in F sub y, we can have a net force. Now, we have the, remember mu, that is the mass per unit of length. Here we have the proportion of F sub y divided by F. Actually, let's say this is F sub 1 and this is F sub 2 in the y direction. So F sub 1 in y divided by F has the same proportion as the slope. So here the slope is the change in y, partial derivative of y, with respect to x. Here evaluating this at the point, let's say this is the point x on the string, and this is at the point x plus delta x. So here I would say the y on the x evaluated at the point x. And the same for the point 2. We have that the proportion of Fy sub 2 over F is equal to the partial derivative of y with respect to x, now evaluated at x plus delta x. So we have that the net force of F sub y is equal to F sub 1 y plus F sub 2 y. So this is F sub y is equal to yes, F1 here. Now if we want F sub y, we have F sub y1 is equal to dy in dx times F, and Fy sub 2 is equal to the partial derivative of y with respect to x times F, and here it's evaluated at x plus dx. So I have that F sub y is equal to F times the partial derivative of y with respect to x evaluated at the point x plus the partial derivative of y with respect to x evaluated at the point x plus delta x. This is the force on y. Now remember that we have the momentum. Momentum is the mass times the velocity. Here remember the mass is the unit of length, the mass per unit of length times the length. So remember that the change in momentum is the change in mass times velocity, but in this case the thing that is changing is the mass, not the velocity. So we have the change in momentum is the change in the mass here from here to here times the velocity. So I would just have mu times delta x, because here at this point all the mass you can see it as mu times x plus delta x, and here is just mu times x. So I have just the difference is mu times dx times the velocity. Now what is the velocity? The velocity, well, we can put it, or well, the velocity is the first derivative of y with respect to time. You can put it as this. Remember that the momentum is force times time, that is the same as impulse, so here I can put force times time. So I have force is equal to mu times dx times, this is dy in dt, so it's the second derivative, so dy square on dt square, that is force is equal to mass times acceleration. All this is the mass, so mass times acceleration. Alright, now here we have the force. There will be the force on y, and we have here is the force on y, so we need to equate these two equations. So we have f times dy dx at the point x plus dy dx at the point x plus delta x is equal to mu times delta x times the second partial derivative of y with respect to x. Alright, now here if we have the dx, if we divide everything by delta x, actually let me divide everything by delta x and by f. So here I will just cancel the f's, cancelling them, and here I cancel the delta x. So I just have no, actually here I mix it up. Here just a observation. Here I have f1 sub y divided by f, but in this case f1 has a f1 is negative. Here it doesn't matter, I can call this negative force as f sub 1, but the important issue is that it has the negative of the slope. So here I have a negative, here I in this one it would be a negative, so here I had a negative, so it was a negative. So if you see, this has the form of something at x plus delta x minus something at x. So this is like you can say it like as y of x plus delta x minus y of x, or dy of x plus delta x in dx minus dy of x divided by x. So all of this divided by delta x. If we take the limit as delta x approaches to 0, we have that this is the second partial derivative of y with respect to x. Here I don't have any delta x, so it's just the mass per unit of length divided by the force times the second derivative, partial derivative of y with respect to time. Here I mixed it up. And if you see, this has the same form as the wave equation that we derived yesterday. Yes. So remember that just here, instead of having mu divided by f, we have d square y in dx square is equal to 1 over d square of the velocity, d square y on d t square. So they have the same form, just the difference is this. So they must be equal. So we have that 1 over the velocity square is the same as mu divided by f. So I have that f is equal to, I send this here, mu times the velocity square. So I have b is equal to the square root of force divided by mu. and we have again the formula for the velocity. The square root of the force of the tension of the string divided by the mu, that is the mass per unit length. Now this was, in this case, I did it with a transverse wave, but here we did not do any assumption about the shape of the wave, and the general formula we will see on future videos. For example, the velocity of a wave on propagating through the air or something like that, on gases, etc. So the general formula is that the speed of a mechanical wave is the square root of the forces that tend to restoring the system to equilibrium, divided by the inertia resisting to go back to equilibrium. So in our example, the tension of the string is the force that makes that is provoking that after we did the disturbance, etc., everything comes back to the equilibrium. So this is the force in favor of the equilibrium, and it is divided by the inertia that is resisting to go back to that equilibrium. Here the inertia is mass per unit of length. So if we increase the mass per unit of length, we will decrease the velocity. If we increase the tension, we will increase the velocity. Now on future videos we will talk about the speed of a wave on a gas, for example, but we will see that on those waves the forces restoring the system to equilibrium is the pressure, and the inertia resisting to go back into the equilibrium is the density of that gas.